So now let's take these matrices AK and BK. AK is a matrix which has width logarithm of n, and we are computing the Boolean product of this matrix by a matrix of height logarithm of n. And the other dimension is n. So when we are multiplying these matrices, we get an n by n matrix. And by taking element-wise disjunctions of these matrices, we are getting the matrix C. Now let's look at a fixed row of our matrix. Its elements are obtained by multiplying a fixed row of matrix AK by all columns of matrix BK. And in the end, this row happens to be a combination of rows of matrix BK with the coefficients taken from the row of matrix AK. So we take an element here, we multiply this element by all the elements of the first row of matrix BK, then we take the second element, we multiply it by all the elements of the second row of matrix B, and so on, and then we take component-wise disjunction of the resulting vector rows. So our idea now would be to use the fact that A has very small width. So the length of each row of A is just log n. And we can pre-compute all the possible combinations of rows of matrix B, and whenever we look at any specific row of matrix A, we can just look up the corresponding combination of rows of matrix B. The table that stores all these pre-computed values would have size exponential on the width of matrix AK, but as the width itself is logarithmic, well, exponent of logarithm is linear. So let's now do the following. Let's construct a table where we'll have all combinations listed of length log n of zeros and ones, from all zero combination to all one combination, and in this table we'll store Boolean vectors of length n. So these would be actually the combinations of rows of matrix BK. Now if we have, for instance, 1 here and all other zeros, then the corresponding line here in our table will be just the first row of matrix BK. If we have, say, 2 ones here and all other zeros, then the corresponding vector written here will be the disjunction of first 2 rows of matrix B. This would be the disjunction of all the rows of matrix B, and so on and so forth. But now let's recall the idea that we used to construct an optimal universal multiple circuit when we studied circuit complexity. So if we choose the right order to compute all these vectors in this table, then actually each new vector can be computed very quickly. So the 0th row in this table, of course, will be all 0. Then we can compute all the rows with exactly single one. So these would be these 2 rows and all the other rows that contain precisely single one in them. They would correspond just to rows of matrix BK. So first, we fill in the entries in this table which correspond to binary tuples with just single one. Then we fill the entries that correspond to 2 ones, so these would be just disjunctions of pairs of rows of B. So by the time we get to step T, we would have all disjunctions computed of at most T rows of matrix B, which would correspond to tuples here on the left side with at most T ones. And now, when we compute the entries on step T plus 1, we take a disjunction of size T plus 1 of rows of BK, but this disjunction contains a disjunction of T rows and one new row in it. The disjunction of T rows can be just looked up because we have already computed it before, and we just need to take the bitwise disjunction of a vector, of a corresponding vector, somewhere else in the table with some row of matrix B, and thus for each new disjunction at the step t plus 1, we need big O of n bit operations. So if we use this order of filling in this table, then we spare big O of n bit operations per each entry in the table. So the number of entries in the table is 2 to the power of log n, which is n, and to compute each entry we use big O of n operations, so we can fill in all this table in big O of n squared time. And so now, after we have computed this table in quadratic time, we then fill the resulting matrix by just going top to bottom just through matrix AK, looking at each row of it, looking up the corresponding entry in the table, and filling in our resulting matrix top to bottom. So this proves the bound of the algorithm. The other great thing to note is that on many modern computers we have vector computations available. So we can work with reasonably large Boolean vectors as a whole, not with bitwise operations. And so if we had an ability to perform each new computation of each new entry at step t plus 1 as a vector operation, so when we take some existing entry which has been computed before and some row of the matrix BK, and we take bitwise disjunction of these two vectors. So in many real-life cases, we can actually make it a vectorized operation, and thus it can be done in constant time. And so instead of this big O of n squared, if we allow for vector computations, we can get the time big O of n here. And thus the ultimate time of our algorithm for the multiplication of original matrices A and B would be big O of n squared over log n. But of course, under assumption that we are able to use vector computations. So let's finally recall the complete scheme of our algorithm. So the speed up was due to the following idea. We have split our original matrices A and B into very small strips, very narrow strips of logarithmic width and height. And this logarithmic width and height allows us to completely pre-compute some data, even if this data is exponential on one of the dimensions of our submatrices. As we have chosen the dimension to be logarithmic, the exponential function of logarithm is still reasonable. And this technique of splitting the problem into subproblems of logarithmic size and pre-computing actually helps in improving time complexity of many other algorithms, not just for matrix multiplication. And oftentimes when some algorithm is being proposed, then sometime later people come up with this kind of technique applied to reduce the runtime of the algorithm by a logarithmic factor.